Hi, so today I'm going to be talking about towards integrated tactile sensor motor control in anthropomorphic soft robotic hands. I'm Nathan Lepora from the University of Bristol, Bristol Robotics Laboratory. So this is an ICRA paper, the name just said, multiple author paper. Many of us contributed to this, and it was, as I mentioned in a minute, it's a collaboration between University of Bristol and University of Pisa and IoT. Um, what this work is about integrating the tactile sensor that we fabricate and examine in our lab, the Tactile, a biometric optical tactile sensor, about integrating that into a human-sized anthropomorphic robot hand, the PISA IIT soft hand. So it involved the miniaturization for the first time, getting our tactile sensor so that it's the same size as a human fingertip, which we consider to be an important stage in the development of this technology. So there's a related IROS 2020 paper from last conference that Ben Ward-Cherrier wrote and presented, which is a similar study to this, but instead the focus was more on a neuromorphic tactile sensor, where we used a neuromorphic camera in the hand, whereas this study today is with a more conventional digital tactile sensor and with more of a focus on the control of the hand. Okay, so the Tactile Robotics Group at Bristol Robotics Laboratory, which I lead, investigates 3D printed soft biometric optical tactile sensors. Because it's 3D printed, we can make them in a variety of shapes and sizes, and we've investigated the integration of those tactile sensors with a variety of robot hands that I'm showing here, culminating with this anthropomorphic hand from PISA IIT. So this is the PISA IIT soft hand. So it's a soft anthropomorphic robot hand, and its design is based on the postural synergies of human hand motion. So this particular hand has just 1 degree of actuation, 1 motor, but with that motor, the tendon layout and the design of the hand means that the hand closes in a natural way that's aligned with the major postural synergy, i.e. hand closure and to wrap around an object of the human hand. So the softness and the interaction with that postural synergies means the hand is highly adaptable to grasp and pick up a variety of objects, as it's been shown here in this video demonstration from that lab. And I emphasize again, it just uses 1 motor to control the hand to result in what appears to be quite sophisticated hand movements as it picks up the object. So we would consider that an ideal complement to the biometric tactile sensor that we develop in our lab, because the key feature of our tactile sensor is that the morphology and the transduction principles of the skin that comprises the sensor are based upon analogous transduction principles in the human skin relating to these dermal papillae. That the mechanism by which contact is transduced into a tactile signal that in our sensor is picked up with a miniature camera. So what's our contributions? Firstly, the miniaturization and integration of a soft biometric optical tactile sensor, our Tactile, as a fingertip of the PISA IIT soft hand. Secondly, the closed loop control of the soft hand using the tactile images that are taken off the tactile sensor. And we're going to give 2 different examples of closed loop sensor motor control. Firstly, kind of analogy of a simple reflex with some basic processing of the tactile sense. So that simple reflex will basically give a kind of a light contact when it closes on objects. And then secondly, a more fine control where the tactile data is being processed here with a convolutional neural network to get information about the nature of contact, so that nature of contact can be controlled. So reporting firstly on the integration of the tactiles of the BRL Tactip into the PISA IIT soft hand. So we use multi-material 3D printing to assemble the parts for the fingertip. So this is the overall design, which, as you can see, is kind of a pleasing integration with one finger here of the soft hand. In particular, we made sure that the design of the surface of the tactile sensor was close to the original design of the distal flange of the soft hand to keep, the interaction of the original soft hand similar to the interaction of this tactile soft hand with objects as it picks them up. So there's basically a modular design to the sensor so that the skin and the housing for the skin are printed as one piece with multi-material 3D printing, and that attaches onto a base unit which houses a miniature camera. The camera is very small. It's a few millimeters across, and the circuit board is, maybe 12 or so millimeters in length, which is basically the key technology that enables the miniaturization of this tactile sensor to be of a similar size to a human fingertip, so it can fit on this anthropomorphic hand. So this is the overall design of the hand, but this is the overall hand integrated with the tactile sensor. So as you can see, it fits flushly as a fingertip, as a human-sized fingertip on this human-sized anthropomorphic hand. An example of the hand in action. So this is just to gather tactile data on. There's no closed loop here, but this just shows the hand being closed onto a stimulus, and then the kind of tactile data that you get off it, which is typically an image of the markers, these markers on the ends of the pins. That I show here, and in the left condition where the finger hasn't contacted anything, these are like the undisplaced original positions of the markers, and then you can see here clearly when the fingertip has contacted an object, the marker's been displaced, and in those displacements are the information about the contact of the fingertip onto the object. Okay, so this is the sensorimotor control algorithm. So it's a typical feedback control algorithm. There's a number of software components in here, from the processing of the tactile, capture and processing of the tactile data, which is done in Python, and then the controller in Python as well, simple feedback controller. And now the native software for controlling the soft hand is in Simulink in MATLAB. So there was an interface between Python and MATLAB to enable that communication. So this is something we're working on now, of basically having a completely Python-based solution for this. And I say there's two controllers we consider. One is simple reflex control of the contact, where we use the structural similarity index as a measure of the deformation of the tactile image, and then the fine sensorimotor control, where we use a convolutional neural network to predict contact state. Now, in terms of the simple reflex control, the way that works is we have a controller error, which we set as being equal to the structural similarity index measure, and I'll explain what that is in a minute, between an undeformed tactile image, so if you like, when the tactile sensor is not contacting anything, and then the image that comes off the camera as it's contacting, the deformed tactile image. So what the structural similarity index does is it does a measure of dissimilarity, actually similarity between these two. So when this is compared with itself, it'd be 1. When these are completely dissimilar, it becomes 0. So that gives an error measure that you can use in the controller by taking 1 minus the structural similarity index, which we then use in the controller we have a proportional controller to modify the motor command based upon the difference between this error from structural similarity and some reference error, which is, if you like, which defines the desired contact strength of this sensor on an object. So in the controller, this works. We picked a kind of a value of a 0.75 for the amount of dissimilarity we would like, and then you see the controller basically ensures that when the hand closes onto an object, it contacts the object with a light touch and maintains that light touch from then on. And so why did we use the structural similarity index? So this is a measure that's being used widely in machine learning and deep learning now. And basically, it's a far more robust measure of similarity than, say, taking the pixel by pixel RMS error. Basically, the pixel by pixel difference saturates very easily, whereas this gives a more gradual description of the change between the two images. Okay, so here's an example of simple reflex control. The hand when using that. So using that controller, as you can see, it basically works to maintain a light contact on these various objects without knowing anything about the object it's holding. Here's how we do the fine sensorimotor control. So instead, we use the convolutional neural network to predict the contact depth and various other state parameters when the hand closes onto a particular stimulus, an edge stimulus in this case. So we're able to predict the contact depth and the angle, orientation, the edge, so on. But in this work, we only use the contact depth. For more description of that, of how we did this, we've got another ICRA talk on optimal deep learning for robot touch and training pose models. So I'll refer to that other work. But basically, as far as this talk is concerned, we can extract very accurate pose information from the tactile sensor using a convolutional neural network. So here's one example of that working. As you see, it maintains, what it's doing is it's maintaining a desired contact of about 2.5 millimeters contact depth. Okay, and then here's another example that works. So here's what it's doing is it's changing the reference, the desired contact, in 0.5 millimeter steps. And you see it's got an accuracy of about 0.1 of a millimeter according to the predictions of the network. Okay, so to conclude, we've integrated a soft biometric optical tactile sensor into the PISA IIT hand, miniaturized to fingertip size, demonstrated closed loop sensorimotor control, both for simple reflex control and fine motor control. We're currently limited to one tactile sensor. We're working on extending to 5 fingertips, and the control and demonstrations were also limited. And we're in here to basic validations of the technology, but we're looking at more sophisticated tasks involving control of the soft hand, bearing in mind that the soft hand has just 1 degree of freedom. And then I'd like to say thank you to the people who do the work, rather than I just talk about the work. These are the people who do the work in the lab. So thanks to my research group at Bristol Robotics Laboratory.